So today we are going to discuss a force method application on this beam ABC, but how we are going to do it with applying a hinge, right? So we introduce a hinge. So earlier we did the statical indeterminacy of the structure is 2, right? So we removed MA and MB and make it simply supported and did the example using force method. And as well as if you want, you can remove RP and RC and do the same example, right? So here we are not going to remove actually any force. What we are doing is at each joint, right? So here bending moment about the free end is 0, right? There's no doubt, right? There's no doubt that bending moment is 0, but you don't know this bending moment, right? So actually here also you don't know the bending moment. So if you draw the bending moment, so this is not the exact shape, right? So if you draw the bending moment curve, probably it will look like something like this, right? So here you don't know the value, right? Here also you don't know the value, right? Let me call this Z, X, you don't know the value, right? But you know the sigma M is 0, right? Sigma M. So that means here it's a and clockwise bending moment, here is an anti-clockwise moment. So probably this is what is this called? A hogging moment, right? Right? Hogging moment. Here also a hogging moment, right? This is the right left end of this part. So it's a anti-clockwise moment, right? So but still you don't know. So if you know the any of this value, so this is minus x then, right? Okay, so those are equal and opposite, but you don't know any of these values, right? So now what we are going to do is we bring down it to 0, right? We bring this point to 0. How we are going to do that? And we drop this to 0. How we are going to do that is, if it is an end, if it is an end support, so probably it will look like a fixed or roller or pin. Okay, if it is fixed, okay, we can simply make it by using pin or roller, right? Then you release the moment. It can rotate, right? If you make it, it can rotate, right? So if it is an end, you don't need to worry. You just need, how we are going to release the moment is, you just apply a pin support here. So then you release the moment. It's like you theoretically, you literally removed MA, right? So that's something else, but still RA is there. But moment you remove that, this RA and the next RA is not same, right? So the structure is not the same anymore. But for this internal support, that's the problem. So how we are going to do this one? If it is an end, you can make it pin or roller, right? So if you make it pin or roller, so probably the bending moment is 0 because the end, right? Sigma M is 0, but you have only one end, so that means only one bending moment is there, and that is 0. But here sigma M is 0 for these two. Sigma M is 0, right? Here it's not, right? So for these two, in order to do that, you need to make these both 0. So how we are going to do that is, you make a hinge here. So if you apply a hinge, so your beam can rotate separately. If you apply a moment, it cannot resist bending. Okay, so the beam, so if it is a, so now it is a continuous beam, right? If this beam bends, right, if this beam is going to bend, if this beam is going to bend over a support, let's say this, so even if it is like this, so this continuity is here, right? Relative to this part is straight. So if it is theta, this is also theta, right? So the relative rotation compared to this part, this part has rotated how much? Compared to this part is also in line, the same line. So the relative rotation is theta minus theta is equals to 0. If this has rotated, if hinge is there, if a hinge is there, so it can rotate separately. Maybe this part like this, maybe this part like this. So it is 2 theta, and here it is theta. So the relative rotation is 2 theta minus theta is theta. So the moment you put a hinge here, right, the beam is not continuous, right? If a continuous beam, it cannot bend like this. So it keeps the continuity even with rotating, right? So that relative rotation is always 0. Remember the term relative rotation, okay? Okay. So moment you apply a hinge, it can relatively rotate. So it's no longer continuous. Let me show you a video. It's actually good. So here's the thing. So get this concept. So this is a continuous beam, right? This is a continuous beam. So it is continuous over here. So that means over this at this point, sigma m is 0. Moment at that point, if you sum it up, it's 0, right? So that means if you load it, it bends like this, right? So it keeps the continuity, it keeps the straight line, right? So it's continuous. The relative rotation is 0. Compared to this part is also in the same line. Compared to this part has not rotated relatively. Those are in the same line, right? Okay. So even you add another loads, so okay. So the bending moment acting on these points are equal and opposite, right? That's obvious. It's in equilibrium. But what happens if you so sigma m is 0, right? Yes. So what happens if you insert a hinge here? So if you insert a hinge, okay, if you insert a hinge, see what happens. The support is also there. Even if it support, this can move relatively, right? Can you see? This part moves relatively. Now there's a relative rotation. Compared to this part, this was the original line, right? This was the original line. So this is always relatively. So think about two of you are there, you moves, right? You moves, but you can see the other one is moving from you, right? It's like that. So he moves, this part moves, but compared to that, it sees the right hand part moves in this direction clockwise, right? It was originally here, but now it's here, moving clockwise, right? There's a relative rotation. It can move independently. That's a hinge, right? So it cannot take any bending moment, right? It cannot take. So if it can rotate simply, it's like a door, right? When you look at from the top view, right? So what happens is whatever happens, here the bending moment is 0. Why? It can rotate freely, independently, but here it cannot, right? Because it is continuous, right? To move, rotate this part also should rotate. So there will be a resistance. Here it's not like that. They can individually rotate. So bending moment is 0, bending moment is 0, right? So this is the hinge, right? At a hinge, both of bending moment at the left hand, the right hand end and the left hand end are 0. The thing is, again, just see, they can move relatively, right? So there's also always a relative rotation if you introduce a hinge. So I will introduce a hinge here, but if we are fixed, we can bring it the bending moment 0 to using a pin support, right? So this is my structure now. I make it hinge here, right? Okay. You saw that, right? So now it's not continuous even, right? So this part can move relatively, right? This part can move relatively. So you remember the hinge here, right? So that video showed you, right? So here you bring the moment 0, but still R, I will call it RA, we'll call it RAS. Okay. So here RBS, and here RCS, right? So I'll take the clockwise rotations positive, right? So now, so the clockwise rotations and the, so we are working under force method. We deal with the bending moment. So the corresponding displacement is the rotation, right? So at the end, we working with the compatibility shape of the structure using force method, right? And we solve for the unknown forces, right? So I take the clockwise moment positive, right? Okay. Okay. So here moments are, so here you need to add this anti-clockwise. Why? Because I'm considering always the left end of the beam. So if you know this value, this is equal and opposite to this value. So I know I don't need to consider this one, right? I can simply go with this one and this one, right? So I will choose this as my first coordinate, this as my second coordinate, right? Where I bring them down the moment to 0, right? So this is my primary structure. Okay, so this is no longer the original one, right? So this is my first redundant coordinate, second redundant coordinate. So my forces corresponding, those are actually the bending moments. Okay, so the F matrix is F1 and F2. So that actually represents what? MB and MA, right? So this is the actual one in the primary structure. This is for the actual structure, not for this, right? Not for that. This is for the actual structure, right? So this is the first coordinate. This is the second coordinate. Here I drawn it for your convenience to understand, right? So here bending moments are 0, right? You can see MB is 0, this is 0, right? So can so if you introduce a hinge here, so in the primary structure, these at the first coordinate and second coordinate, you don't have any bending moment, right? 0 because of the hinge, right? So this is for the original structure. Again, I will draw this one. So this was our original. Right? Is there a roller? Yeah, roller. Yeah. So this is my first coordinate. This is my second. Second is actually MA, okay? Right here is RB. Sorry, MB. Right? So what you are going to do is you just, so you have the loading as well. You just apply a hinge, right? So you change. So at the end, you just need to pin support, right? Because that's anyway going to make when the moment 0. The thing is internal supports, right? So what you are going to do is, here you can simply take it as converting it to a pin support, right? Can't make it roller because it's unstable. You need to have some structure, right? Otherwise it can move to the infinity, right? So there's a hinge, right? So your loading is here. So it can move relatively, right? It can deflect, right? So this no longer remains. This is the primary structure. So what you're actually going to do is you apply that. So this is actually the displacement, right? So here there was, so this is moment. Actually it is something it's continuous. So you remember the relative rotation. If it is continuous, relative rotation was 0, right? Beam is always continuous. But with hinge, there's a relative rotation, right? So you always consider this part. So that means compared to this, you should consider how much this has relatively rotated, right? So if it is theta, because these are symmetric, this is also theta, this is also theta. So the total relative rotation is going to be 2 theta, right? Compared to this part has moved 2 theta, right? So this part is, originally it was here, it is now theta. So this relative rotation is also applicable for internal support, right? At the end, you can take the same deformation. It doesn't matter. Why we are taking displacement? Because we are in the force method and we should work with the compatibility. That means the shape of the structure. Original structure, the relative rotation here is 0, and here also the rotation 0, right? Here you have now make it 2 theta and theta. So this is no longer remains the original. So what we are going to do is, we removed the bending moment. Actually we make it 0, but now we are going to give it again. But how? We are going to give a unit moment, right? we are going to give a unit bending moment. Right. So here no loading, because loading is in the primary structure, because ultimately we are going to superimpose everything, right? We are going to give unit moment at first coordinate, first redundant. Okay. So if you apply a moment like this, it would look like this. Okay. So you are again taking the relative rotation, right? So if this is theta, this is also theta because symmetric, right? So the relative rotation, this is also theta. Why this is theta, right? So the relative rotation is 2 theta, right? Relative rotation. Here the relative rotation is actually theta. Why? There's no internal thing, right? That it's at the end, right? Compared to this one has moved so clockwise, right? Always clockwise rotation. Compared to this part had moved clockwise direction, right? This has moved in clockwise. Clockwise rotations are always positive according to a sign convention. There is also clockwise and here also clockwise, right? So then you need to consider actions as well. Here you will see the actions. Let's call it VAS. Let's call this VA. Sorry. VB and VC. Okay. So VBS and VCS, right? So that's a hinge, right? If it is a hinge, you can just separate it from the hinge, each part, because you know the bending moment is 0, right? So if it is W, you know what is this value? WL over 2. This is also WL over 2. This is also WL over 2. So the total reaction at B will be WL, and at the corners WL over 2, right? Because we are at the hinge, right? So here, if you apply a unit moment, right? So you need to determine, still you need to determine the displacement, okay? At each step, you need to determine the displacement and the actions, right? So here at the as actions is okay, displacement here 2 theta and here theta. So you need to take it from the appendix. I'll show you how. So here also the relative rotation 2 theta, it's not the same theta, so I will make it 2 alpha. Okay, otherwise you will be confused. I'll make it alpha. This is 2 alpha, right? Right. So this alpha Okay, so the displacement, these are actually displacement. So F equals kx. So these are the displacement for a unit force, right? Unit moment. So what is this actually? Displacement is going to be 1 over k, right? So that means these are 1 over stiffness. Sorry, 1 over stiffness means flexibility. So that's why we use simple F term. Simple F is okay. Actually, it is a displacement for a unit force, right? So here the actions you have to take, right? So you can just take, if you apply, you can separate, still there's a hinge, okay? Like this. You don't have any loading. It's just one bending moment, just unit bending moment. Okay. So your reaction would be, so this is L and this is L. So you can take bending moment about this point. 1 is equal to this force into L, right? So it would be 1 over L, right? So this would be, so the taking vertical equilibrium, only these two are the forces, right? This is a moment. So this would be minus 1 over L. This one also would be minus 1 over L. So altogether minus 2 over L, right? Here and here also 1 over L. Okay. So for the third redundant, sorry, second redundant, so you apply a unit redundant at the first coordinate. Why? There was actually a bending moment and a rotation, and we make the bending moment 0, right? Right. So the relative rotation was actually 0, but now there's a rotation, but bending moment is 0, right? So you are getting, so bending moment is 0, so you are giving one at a time, right? So you are giving, you remove the MB, but you are giving a unit bending moment 1. So actually you have to multiply everything finally by the original MB value, right? Okay. These displacements are for a unit force. So how much it would be actually for MB, right? That's what you have to do. So here we are applying it at the first coordinate, second coordinate. Second redundant. So if you apply, only this part will move. It is not affecting this part because there's a hinge separated, right? So this is 1. So only this will have some reaction. These actions are 0. Why? This part is separated now. So if you apply 1, this is 1 over L, and this is minus 1 over L, right? Minus 1 over L. Okay. So you can take bending moment about this point. This is 1 bending moment. 1 is equal to this force is not coming, this force into L. So that's 1 over L force, right? So you need to take again the displacement occurring, relative displacement. So compared to this part, this has moved, this let's call beta. Okay. So compared to this part, this is let's say this would not be, and again, yes, so these are not symmetric bending. So this alpha is something and this is alpha 1, I would say, right? This is not same, okay? Because if you apply something like this, one here, so this part would bend greatly and it would here, okay? So this is also, if it is beta, this is also beta, no problem, but this is beta naught, let's say, right? So these are the also the flexibility coefficients, displacement per a unit force. And here we consider the MA, and actually we apply one bending, one unit of bending moment, right? So the actual bending moment is MA. You have to multiply everything by MA, right? Finally. And once you get this relative rotation, you can add those at each joint, right? At each joint. So you know, here actually the relative rotation is 0. And here also continuous beam, relative rotation is 0, right? So you are checking the original beam's shape at that 2 point, right? So you are going to do it like this way. So I have already found the action, so I don't need to. So I will again consider it. So my primary structure. Okay. There's a hinge, right? So the relative rotation. So this is symmetric bending. So this is theta, and this is as well, right? This is also theta. Okay. So can you see the relative rotation actually? Okay. So compared to this part, the rotation is 2 theta in clockwise direction. It is the relative rotation, right? Relative rotation. So compared to the original position, so this is considered to be the original position. Okay. Compared to this part, because this part and this part was perfectly in straight line initially. So now this has moved relatively 2 theta in clockwise. This has moved relatively 1 theta in clockwise direction. So this you say F1, sorry, coordinate 1 and coordinate 2. So the displacement at coordinate 1 due to the unit redundant at 1. So here, not actually here. So the flexibility, don't forget that, right? So here you need the actions and the forces, displacement. So the displacement D1 how much? 2 theta d2 theta. Okay, so we can find the displacements from the appendix, right? Okay, so if you apply a moment, right? Not here. Okay, sorry. It's actually unit W loading here, right? So those are hinge separated from a hinge, right? So they are acting individually, right? So you remember, just remember this. Just remember this one. They are acting not continuous, so they can move relatively, okay? It's a hinge, right? So if a load is applied, so you can just take it as simply supported two spans, right? It's like this. Initially it was like this. So if you apply a hinge and here, so simply support, you can just take it as this, two parts, right? You separate it from the hinge because those are bending separately, right? So each part is symmetrical, right? Because the load is uniform and the rotation is at the both ends theta, right? So you need to know what is this F4, right? So F4 and F5, right? So the F4 is QL over 24 EI, right? QL over 24 EI. Okay, this is QL over 24 EI. Now it's multiplied by 2, right? So it's W L, I don't know, it's L cube or something. Let me see again. Yes, it's sorry, not here, L cube, right? F4, this part, right? It's QL over 24 EI, QL cube. Here our Q is actually W. So 24 EI into 2 multiplied by, so it becomes 12 EI, right? Here actually 1 theta, so it is WL L cube over 24 EI. So our displacements are okay. You got the force as well. So that is action matrix, you remember? Yes. And BCS, right? So what are those actually? So we calculated BAS is WL over 2. This is WL contributed by both ends. That's why this is WL over 2. Yeah, can you see? So our first part is okay. We find the actions, find the found the displacements. So our primary structure is done. So we need to go and apply the redundant at first coordinate. Right? So if you apply the redundant, so clockwise is positive, right? Because we are considering this part. So this is exactly opposite and other. So here also clockwise positive. So if you apply unit moment, okay, unit moment. So this would look like this. Not here only you are applying. Unit moment at first coordinate. So you can determine this theta. So it is, so if it is alpha, this is also alpha, and this is also alpha, right? Let's say this is beta. So the displacement is, so here not the actual displacement, these are displacement for a unit force. That means flexibility. Flexibility at first coordinate due to the redundant force at first coordinate. This is the coordinate, this is the force redundant acting coordinate, right? So that is 2 alpha, right? So here displacement at second coordinate due to the redundant at first coordinate. So that is beta, right? So we can go ahead and find what is alpha and beta from the appendix. So here can you see, if you apply M, so the nearest deflection rotation is F1, it's ml over 3 EI, the far end is ml over 6 EI, it's half, right? So M is equal to 1, right? Because unit moment, we are checking the displacement, rotation actually. Why? We need to consider the compatibility shape of the structure. Right here it's 2 into, so ml over 3 EI means M is 1, so L over 3 EI. So here it's L over 6 EI. So from the appendix, you only take the value, right? From here, you consider the sign because these two are always clockwise from the original position. From the relative displacement is also clockwise, right? Compared to this part is clockwise. So these are positive, right? 2L over 3 EI and L over 6 EI. And yes, action matrix, action unit. So AU, action at, so the action coordinate are different, right? So the first action VA is at first coordinate here. These are action coordinate. Okay, these are redundant coordinate. So those are different things, right? This is action coordinate. The actions we are monitoring, right? Action at 1 due to the redundant force at 1, right? So the action, unit action at unit action at 2 due to the redundant force at, still redundant force here at 1, right? So the action unit matrix at action unit action, action at third action coordinate due to the redundant at first, right? So this is equal to, so we calculate it again. So 1 over L upward. So we'll take upward positive. upward positive. So this is 1 over L. This is minus 2 over L. This is 1 over L, right? And yes, we are done. So our actions are okay. Displacement, so actually the flexibility, why? These are the displacement per a unit force. So this is going to be finally multiplied by everything by MB, right? So then we are getting the corresponding deflection. If this is for a unit force, what it will be for MB force, right? Very simple. So we are applying the second redundant now. It's here. Right. So we are giving the clockwise moment of unit moment, right? So we will say this is alpha. Okay. This part is not moving, right? Because there's a hinge, right? Hinge is there still. So hinge is there. Okay. So yes, the relative rotation of this is alpha, right? So the relative rotation, it is clockwise compared to the original position. It has moved clockwise direction compared to this part. This part has moved. That I would say this is gamma, right? So finally, we need to consider what's this, right? So the displacements. So the flexibility, that is the displacement rotation actually here. Why these the forces are moments, okay? So displacement at first first coordinate due to the unit redundant at first coordinate, second coordinate, right? Theoretically, this is equal to F21, okay? If it is not, you might have made a terrible mistake, because according to Maxwell's theory, F12 and F21 are equal, right? Exactly equal with the sign as well. So F12 you can determine. So here you are acting the bending moment at here, right? So you remember F, that is F displacement at 2 due to the unit force at 2. So you remember that was ml over 3ei. So m is 1, so it is L over 3ei, right? So the far end you saw ml over 6ei, right? So both clockwise, relative rotation also clockwise. So it's L over 6ei. So our flexibility coefficients are okay. So you need to determine the actions. AU, action at first coordinate. So this is our first action coordinate, first, second action coordinate. These are third action coordinate, right? So we are taking the actions. So these are the unit redundant coordinate. This is 1 and this is 2. So our redundant per MB and MA, we make it to 0, and actions were VA, VB, and VC, right? But here it's not the actual structure, okay? So I just remember those only. So action at unit, action coordinate 1 due to the unit redundant at second coordinate. Actually, 1 and 2 are the same, right? A. So this is action unit at action coordinate 2 due to the redundant at 2. right? So this is action coordinates, action unit at third action coordinate due to the redundant at 2. So what were they? We considered this is -1 novel, 1 novel and 0. So altogether 1 novel, 0, right? -1 novel, 1 novel, 0, right? So now you can write the displacement, right? So here actually displacement is, so in the force method, we are doing actually the shape, your original structure, the first coordinate, the relative rotation is 0 because there is a continuous beam, right? So original displacement is 0. At A also, second coordinate is also 0, right? So the primary structure, you had WL squared over 2LEI, WL squared over 24EI, displacement, the shape, right? At the first and second. So you can take WL squared over 2L out. Sorry, you can take 24EI out. Is that so? Yes, right? No, you can take, yes. So what's this? This is 2 and this is 1. Okay. So here you need to, so this 2 alpha is for this 2 alpha is for a unit. This is for a unit moment, right? This is for a unit moment, but the actual displacement, the actual force is mb, right? So you need to multiply simply by mb. So F11 into mb at first coordinate, right? At the second coordinate, how much? F21 into mb. This is the first redundant structure, right? At the second redundant coordinate, it's at the first coordinate, it's F12 into actual value is, everything should be multiplied by MA, because the redundant is MA. Actually, we are applying a unit moment. If these values are for a unit moment, what will be for the actual bending moment, right? F21, F12, sorry. So you can take this part out, right? To the others. No, that's okay. So this, you can form a matrix. This is actually 0. So this is, you take as F matrix, flexibility matrix, and this is force matrix. Okay. This does not depend on the external loading. That's why we use a square bracket, right? So simply we need to find this. We can put it here, and this is we call D matrix. So it is going to be minus D. It is in the other side. So you need to multiply it by F inverse to find force matrix. So the F inverse is, so F11 is how much? 2L over 3EI. So you can take it out. L over 6EI. L over 6EI. L over 3EI. Right. So you can take the common term out. So what's that? L over 6EI. In such case, inside term would be 4, right? Is that right? 4, and it's 1, 1, this is 2, right? So you can make it K and put it back. So F is going to be 4K. So you again push it to inside. So the determinant is main diagonal minus subdiagonal. 4K into 2K, 8K minus K squared. So it's 7K squared. And the F inverse is, so you need to interchange these two. And multiply these two by negative value. And divide it by the determinant. So 1K is cancelled. Okay. F inverse becomes 2 minus 1 minus 1, 4 over 7K. So you can apply the K value. It's L over 3EI, L over 6EI, okay? Okay, so your F inverse would be 6EI over 7L, right? So this is F inverse multiplied by minus D matrix. So it's is equal to F matrix. So what's this? So you can see this EI is cancelling. 1L is cancelling, right? So it becomes, so this is cancelling. So it becomes W L squared negative over 28. Okay. Into how much? 2 into 2 multiplied by 1 into -1. So that means 2 into 2 is 2, 4, 4 minus 1 is 3. So 1 into -1 is -2 plus 4. It's plus 2, right? So it's going to be -3 WL squared over 28 and minus WL squared over 14. So this is actually MB and MA. So how to write this? So you remember original matrix. So we found MB, we only consider this part, right? So in this part minus, so that means it is anti-clockwise. So that means the other half it's clockwise, right? We know this value, right? It's is. So here also it is A also anti-clockwise. So you can just go ahead and separate it and find the actions from here as well. If you want, you can find it on the matrix as well. So even the action in the original structure is equal to actions in the primary structure, right? Plus action unit matrix into F. The same way, right? Same way you have to do. These actions are equal to this action plus these are for a unit force. So you need to multiply the actions by the actual force. And when you simplify this, there will be, here will be the actions of the, so I will write it, no problem. So here it's VA, here it's VB, here it's VC. Okay. Okay, so the action of the structure is the primary structure. Yes, action stays WL 2, right? Okay, so from the action unit matrix, actually you have at the first coordinate you have AU11 into MB. At the second coordinate AU21 into MB, right? Likewise you have. So First coordinate you have AU 1 1 into MP, and the second redundant structure you have AU sorry, I will write the first one order. I will go it in order. So it is AU 2 1 into ME. So this is AU 3 1 into ME plus from the second one it's AU 1 2 into MA. This is AU 2 2 into MA. This is AU 3 2 into MA, right? Again, you can form a matrix. This is going to be 3 by 2 matrix into MB and MA. What is this matrix? This is the F matrix we found earlier, right? F matrix you found earlier. Can you see? So it's very easy. So you know this, you know this, you need to find this, right? So I will write this. I can take WL out. So remaining would be how much? Sorry, I can take WL over 2 out. So it's 1, 2, and 1. Okay. So then you need to find the action unit matrix, right? So what's that? Here 1 over minus 2 over 1 over, here minus 1 over. Remember 1 over into force matrix. What is force? W, this one, right? The same, I haven't, it's okay to use something convenient to simplify, right? Minus WL over 28. This is the matrix. Okay, you can simply multiply this by here. So not multiply that, not multiply that, it's addition, okay. So here minus 1 over L. So you can give 1 L to here, right? Because then the L is getting cancelled. That's why. So I gave 1 L to inside, right? So 1 over L into 3 over L, it's 3. Minus 1 over L into 2L, it's 2. So 2 over L is minus 6 plus 2 minus, sorry, plus 3, 1 over L into 3 to 0. into minus WL or 28. Okay, so this is how much? 1, 1, minus 4 and 3, right? Okay, so here as well, I will take a W, this is WL over 2. So I will make it exactly WL over 28. So that means I need to take 1 over 14 from out inside. So that means all the things would be multiplied by 14, right? So 14, 28, 14. So now the common term is same. Okay. Can erase this. Fourteen. So this is minus 1 is here. So 14 minus 1. 28 plus 4. 14 minus 3. So that's going to be WL over 28 into 13, 32, and 11. So this is VA, VB, and VC. So it's done, right? So this is how you use the informing hinge to make the primary structure, right? This is pretty convenient. So thank you very much. Hope to understand. If you have any doubt, feel free to email or whatever.